Today, I wanted to take some time to explore something fascinating that's happening right now. Enterprises are completely reimagining how AI works in the real world, not in labs, but in actual business environments. And it all comes down to production quality inference at scale. Exactly what open source can help us solve. And joining us for this topic today is Brian Stevens. For our listeners, Brian is the Senior Vice President and AI CTO for Red Hat. Welcome to Technically Speaking, where we explore how open source is shaping the future of technology. I'm your host, Chris Wright. You and I go way back. So you're not just here, but you're back at Red Hat. Fun fact, you originally hired me here. So give us a little bit of your view of having been here and then left and done other things and come back. A lot's changed. What's transpired in that time?
A lot's changed and some of it stayed the same. And great to be here. It's great to be, especially working with you and the rest of the gang. I'd say there's a lot of parallels. The first time we were trying to establish a Linux platform for enterprise customers, and the problem we solved for was enterprises back then had to be committed to one vendor. And we built a common version of Linux across lots of hardware and lots of apps that in the early days of Linux, right? The apps only worked on one version of Linux, and we kind of brought all that together, and it really created reach for vendors, but it also created enterprise value. Believe it or not, I'm back here, and I think we're going to be working on the same thing this time, just in AI inference, where there's lots of great accelerators for running AI, and there's lots of great models, but they don't all work on the same common stack. And that's really what I think the next journey is for AI inference to be successful.
The more things change, the more they stay the same. So you left Red Hat, you spent some time at Google, got a lot of exposure to the cloud world. Then you went to Neural Magic as CEO, leading a startup. What drew you from cloud to AI, and what was the initial impetus for getting?
I didn't really have an impetus. I was home writing code and using Google Cloud and enjoying myself, quite honestly. And then, but I met Nir Shvat, MIT founder at Neural Magic, and I fell in love with him, and I fell in love with the technology that they were trying to solve. And they were doing this great thing of trying to bring AI inference to CPUs. The initial phase was the GPUs got it wrong, quite honestly, which is a little, which was not a truth. Meaning that you could optimize models in such a way to make them smaller where they could run really well on CPUs.
Right.
And then it's a great dream. You can bring AI everywhere.
Right.
Really powerful AI.
Totally
everywhere,
ubiquitous.
right?
Yeah.
And then so it was definitely from what we did in our first chapter of Red Hat with Linux and x86, when nobody thought x86 could compete with a high-end processor.
Right.
So we were skipping the step of all the GPUs and going right to the hardest CPUs. And then obviously and that worked really well, but then it was really early for production level inference. And then ChatGPT was born, and that just changed everything for us.
Changed everything for everybody.
Yeah.
It was an eye-opening moment for the world, I think, putting an interface on a large language model that makes it accessible to everybody. And here we are a few years later, and Neural Magic's focused on inference. You've got a deep technology focus in a core project, vLLM. What was that pivot like, going from CPUs to GPUs, from machine learning to generative AI?
It was, you always hear about startups pivoting and whatnot, and like it's an easy thing, and you just go over here. It was tough. It was tough. I mean, we're only 42 people, so I'm not going to paint that it was a massive city. It was a village,
right?
But culturally, it was hard because all the engineers had invested so much in their code base for inference, and then all of a sudden we're saying, well, that doesn't matter. We're going to go over here, and so it was I wouldn't call it disruptive, but it was definitely an emotional thing, right? And then, but it had to happen because the impetus was, we saw like when after ChatGPT, not right away, but the following year, we bet on that open source, maybe the open source LLMs would exist.
Mm.
And as they started to exist, we saw GPUs had trouble running them. They had just gotten big enough where even GPUs, people were using multiple GPUs instead of one to run a model. And we knew we weren't GPU experts, but we were high performance computing experts and machine learning experts. And the team, everybody got brave enough to say, let's go figure out this new world, of GPUs and like really help models run efficiently on GPUs.
And I like that being brave. It takes a lot to jump into a new space. If you got domain expertise in one area, you get, almost your identity becomes defined in that way. The importance of what you learned in sparsification and making models smaller for CPUs, were there immediate lessons that you could bring into the GPU world?
Yeah. Like what's funny is what I've learned in all of this is, the engineers, the ML researchers we had, and then the high performance computing people on the production side, the whether it's a CPU or a GPU is just an implementation detail, but I don't think I appreciated that. You tend to you brand yourself a little bit and you think I'm in this domain, but the reality is amazing engineers are just amazing engineers when you put them on other problems. So yeah, we had to do a couple of things. We had to, on the model side, really kind of invent some new compression techniques to make the models smaller, but just as accurate. Mm-hmm. But techniques that would work on a GPU, which were, let's call them, 80% different than what we were doing on a CPU. Right. Some of them still crossed over. And then on the high performance computing side, which is what we call building the runtime inference stack, we knew nothing about programming to CUDA, which is the API for NVIDIA GPUs.
Right.
And so we tried to hire people and couldn't find them, like the ones that are, so and then
rare commodity.
Yeah. And then the team just got great at it. They just got great at bringing their algorithms to CUDA, and that got us off and running pretty quickly.
And the focus there was bringing models to GPUs, and then there's still a performance optimization. So with sparsification, you're making the model fit well and perform well on a CPU. There's some compression techniques. There's just some raw performance and even flexibility of how you use the underlying hardware. What was your initial focus when you got into the GPU space?
I'd say like the first thing, we had spent 15 months building a serving stack on CPUs for LLMs. So because they process really different than anything we'd seen in the past. So we learned a lot there. We learned all the techniques you need to do for serving Gen AI, large language models. But the thing we decided, but we knew for GPUs, we're probably going to start from scratch. And so the first part was, we picked an open source project. We wanted to go open source this time, on that side. And there wasn't really a lot of choices out there at that time for code bases. And we obviously ended up picking vLLM, the Berkeley project that had just started. But the initial round of optimizations we focused on is that if you can figure out the compression techniques always map to a particular piece of hardware. Mm-hmm. So every generation of NVIDIA hardware out there, the NVIDIA engineers build more instruction capability inside the next GPUs. So you can see this life cycle of hardware. And so you want to do quantization techniques that map to each generation of the hardware. Like we're working on Blackwell right now, which isn't really available mainstream. So we're building, how do you quantize a LLM for Blackwell that recovers 99%? And then at the same time on the serving stack side, on the inference side, how do you write these, what are called kernels, which I know is kind of funny for that. How do you write these kernels that actually run those optimizations efficiently on it? But you can get these, 50%, 2x, 3x, 4x utilization increases by doing it. So it's really important that enterprises have this capability.
One of the things I find talking to customers is making investments in hardware or even cloud instances reserved with GPUs attached. It's difficult for them to get the full utilization of that hardware. So something like improving performance, optimizing the runtime to take advantage of the hardware is super important. I I know we'll get into that quite a bit, but I'm curious, in the very beginning, switching to GPUs and identifying what open source project to get involved with, what were the criteria? What were you looking at? And what led you to vLLM?
I mean, we were proprietary before that on the model serving side. Like all of the optimizations we do to models, we would publish the research. So we look very much like a training organization. We're doing the algorithms for quantization. We'd always publish that research and then commit that code to open source, the tools for it. But the CPU engine was proprietary for reasons that are quite boring, honestly. But this time we wanted to be all open because, as you know, like the world of AI is just full of open. ML people are picking open source tools. They just are. And so we thought we'd have to start from scratch, but the Sky Lab at Berkeley had just, I think a month or two before, June of 2023, not even 2 years old, they just started this thing called vLLM. And they implemented that one first algorithm that you need that's important to run LLMs. So we actually didn't think it would be very popular. We're like, well, then why not like just go invest in that one? And so that's where we started. And then with the idea that it just makes it easier for people to use your technology.
The pivot into GPUs and the optimization and ease of use. So that I think part of this is about putting models into production. This is where that runtime environment to me is so important. And I think we're looking at that as the AI operating system, that next generation of technology. We've built Linux. Okay, you compile your application once, you run it in production many times. Now we're training a model, effectively once, but then you put it into production for inference repeatedly many times. So maybe we could dig into that view of the AI operating system.
Yeah. And you said the thing you said before that it didn't really address is like, how does optimization fit into that production work? And you think about how much work your team does on Linux to make it super efficient. So you got to make it reliable, but you also have to make it really efficient and really make, hardware utilization high. So I think vLLM is fundamentally focused on that part first, maximum efficiency and put your GPUs to work for you.
Yeah.
But to solve for the next one, we found like even at Neural Magic, like early work with clients, that to go in production, there was a gap, quite honestly, of what they had to build. And this is whether they're a big company that's putting inference at scale or whether they're a startup or whether they're a traditional enterprise. And we found like they're all building their own thing. They're building their own scaffolding and framework, right? Unfortunately. And that, again, was another aha moment. Like you haven't solved the problem, right? Just to build a good runtime stack. And so that just began our journey, which started almost a year ago, but like now, like at Red Hat is really starting in earnest, was around how do you bring inference into a Kubernetes world, right? Because Kubernetes is where people are running production level application services. So why wouldn't you bring inference into that world?
Yeah,
for an enterprise.
Well, it makes sense because if it's not a single production workload, it's a whole collection of production workloads. That means you have pooled resources, GPUs managed by some distributed system, Kubernetes. And so how do we bring these two worlds together and maintain that optimal efficiency?
Yeah. So I don't know what the OS is for this whole stack. I guess it depends on whether you're looking up or looking down.
Yeah.
But the Kubernetes, I think, is the Kubernetes meets vLLM is kind of the first principle. And then because you could see this other world where you'd be coming to an enterprise and saying, okay, we got to go do something entirely differently. Here's a cluster and here's another technology for scaling it. And that would be really disruptive and kind of unneeded. And so I think like the integration of like scalable, secure, provisionable, multi-tenant, delivering to SLO inference inside of a Kubernetes environment is exactly what enterprises are going to need.
Yeah. I mean, the vLLM, I think of that as the core runtime, but making it distributed is critical. And as you described, you could do that in a number of ways. One might be a bespoke mechanism to just do distributed inference, for example, or take advantage of all of those hardware resources. But then we'd miss the buzzword du jour around agents and agentic workflows, which bring kind of application logic connected with LLMs and having that orchestrated across a single platform, at least from my point of view, makes a ton of sense.
Yeah. At the core, before we even talked about like how does vLLM have to change for this kind of scale out world and operating system of AI, the core tenet of it is really powerful. I think not often realized is what it does is it brings a common inference platform to multiple accelerators. Not trivial, right? Like and I think that's why VLMs flourished a lot, is because all the accelerators and GPU, builders out there are directly engaging to get integrated into VLM.
Yeah.
On top of that, every model that comes out, every frontier model that comes out, we had Gwen just drop. We've had 4 or 5 big major releases this year already of different frontier models. It's crazy. And but every one of them, we always hear about like weights and they get bigger and smarter, but they also develop new structures and new techniques, right, inside the model. And that's what makes them have these more capabilities and be more efficient. All of those have to be implemented inside of VLM. Right. Every time in a compatible way, of course, right, going forward. And so there really is this nice relationship with all the frontier models that are coming out with VLM, and it works really hard to enable it, just like we did with Linux back in the, we still do with Linux for like the top performant applications. But that's where you see this emergent kind of kernel, right, in your words, for the platform, that is cross hardware, cross model, which is, all the vendors win with that because they can reach the market, and then enterprise wins because they can consume everything really kind of simply.
To me, that's the beauty of open source. It's that creating the sort of de facto standard technology building blocks that in this case brings together the hardware world and the model world, where you can run optimized models on any hardware, choose your model. There's a lot of choice, especially as more and more models are coming with open source or at least easy access type of licenses.
Yeah.
And that solves for any model on any hardware. So then we switch gears into that. These are big models sometimes, and the core implementation of vLLM is around a KV cache. And
you went there, not me.
We love technology. And so I think the next view of vLLM is about really distributing the KV cache and building all the optimizations that come along with that. And how do you see that evolving?
You wouldn't think it, because there's often these application-centric systems that you scale them by replication and load balancing them, right? Just at n servers instead of one server, and you get n time scalability. Yeah, that kind of tier. As we've learned, LLM serving's different than that. You could do it that way, but you won't have maximum output in 2 different dimensions. One, it's really hard if you always have to serve one model on one system. It kind of limits the flexibility that what you talked about, is like, because people run big models as well, right? And so you really want the underlying system to be able to run a model across 1 GPU on one server, 8 GPUs on one server, or GPUs across multiple servers, all participating in the same inference request. Right. And so that's kind of one for meeting those service level objectives of the users that you're serving, because they have expectations. And then the second is around efficiency at the hardware level. So it's really complex on how VLM has to think about all of that. And then what's happening further in what you just talked about was to support all that, you have to end up having distributed services in this KV cache, which is on behalf of one inference request. You now want to replicate that across lots of servers. And that sets you up for this world where any server can respond to a token request. Right. If any server can calculate the next token for you because it has pure state of the KV cache, you get all this flexibility on different ways of meeting service level objectives for customers while increasing the number of tokens you can produce per unit of infrastructure. So it kind of like all comes together in terms of the distributed inference world.
I think it's, for one, it's super exciting. Like the building blocks, the OS vision, I'm obviously aligned to that with my Linux history. Distributing that, those are always the hardest problems in computer science. And then thinking about what that enables. So it's not just technology for technology's sake, but this is building that multi-tenant, multi-model inference capabilities pooled on hardware. And if we go back to the potential of something like agentic, which has multiple models working together on a common workflow, it's clear you have to have scheduling and sharing of resources, and it starts to look like this whole distributed infrastructure and distributed application world that we understand pretty well. So I think there's a lot in this optimization space that vLLM plays a critical role, but there's probably more around coordinating all of that. How do you see that working together?
I mean, you alluded to the first core piece is obviously there's VLM, and how does VLM have to change? Actually, it has to change to integrate into this distributed KV cache world. So there's that's like the core project. It's also dragging in higher performance software for data distribution across servers. Trying to leverage what's been out there in the past, but there's also some new things that are very LLM specific that are being built, and that also integrate with all the different fabrics, hardware fabrics that are going to be very heterogeneous that enterprises have. And that's kind of the bottom half of the stack. And the top half is with that, and it's almost like a layer violation in my, as like a furious, like, and you know where I'm going with this, is that now you want the routing of new requests coming in to be very aware of like that distribution of KV cache for different users, which usually you wouldn't do that, right? You'd be like, no, this load balancers should just know about least loading and things like that. Your desire is that you send it to a system that has to do less calculations because it's already got the cache. And then that's another level of not just speed and performance, but it's also increases what your infrastructure can produce because it's not relying on the GPUs.
Eating the same multiplications over and over.
So all of this is coming together, to be honest, in kind of the next generation distributed AI inference capabilities.
First of all, it's super exciting, and especially how quickly it all moves. And then second, we touched a little bit on agentic, but if you look at other techniques for making models better, we have scaling limitations in data. We talked a lot about the data wall in the industry and how much data you can put into a model to improve the outputs of the model. Really, the current focus is moving more towards inference-time scaling. And that puts something like vLLM right in the middle of the picture. When you take inference-time scaling connected with reasoning capabilities, this is all about the importance of inference and optimization and that distributed picture that you were describing.
That one was kind of a surprise to me, to be honest, because in the past, the whole thing is smaller models, right? Fine tune them, get the tokens right first shot. You know what I mean? Always get the answer by doing as few calculations as possible.
Right.
And now all of a sudden, we're building these models that build all these intermediate state tokens, right, to get you to the final answer. So now the final answer is coming not just from call it a larger model, or at least a reasoning model that's producing far more tokens than what you'll ever see. And so that you think of what that requires on the platform side is, all of a sudden the tax on the platform to deliver that, the cost per token's gone up. Right. But we've already realized that's produces better, higher quality answers. So it puts even more of a burden on, you better be as hyper efficient as possible. Right, for an enterprise and their infrastructure. And that's why I think they really need this kind of capability. And you just said there's just all kinds of different agentic workloads different size models, reasoning, different QPS rates for different demands on each of those.
Yeah, which is why I think vLLM is such an exciting project, and that inference space is so important, and taking it from the core kernel to distributed and then solving all those hard problems along the way. You've got all the hardware vendors that you mentioned. You've got the different model providers coming to, we work together to build optimized models on day zero when they're released.
Yeah.
How do you see that coming together at this broader community level?
I've been like, and this is kind of ironic, I've always been, it's more about the ecosystem than the technology. And I know that's as you and I work together on the technology part of that, just meaning the picture that we're painting here shouldn't just be, I don't think a one vendor approach would ever be successful, whether that's proprietary or open source, quite honestly.
Yeah.
And I think it has to be one that is cross-industry, all the accelerators, all the model providers. Now we're talking about like network interconnects. We're talking about, server manufacturers. It's everybody, right? It's the agentic platforms and how they integrate. And so I think like there's one path is land some open source project out there and hope people notice it and want to build around it. And then there's another approach that says, let's bring the ecosystem try to get the ecosystem and like-minded people together, even if they compete in some aspects of their business, get everybody together with this common spec of what we've been talking about for distributed inference, and let them go build it shoulder to shoulder.
We've seen that work well in the Linux space. We've seen it work well in the Kubernetes space, like this classic co-opetition. We work together in communities. We find different ways to compete in the market commercially.
Yeah.
But it builds better technology into this robust ecosystem that you described. I don't always think of it that way. I think of a de facto standard technology, but bringing it outside in, all the people come together to build the...
Yeah. It is true that because they've got diverse opinions.
Yeah.
Right. And the one thing I love about developers generally, but open source developers that are used to their own opinion might not be the one that lands. Yeah. It's shaped in some way. Yeah. Right. And I think like tackling what we've just talked about is probably one of the biggest, not just projects in open source AI, but probably could have a really large impact on whether or not it works at all for enterprises. Because I just can't imagine this world where enterprises are in a DIY mode and 20 different platforms to deploy 20 different accelerators and 20 different models and can't drive to the next level of efficiency, and therefore AI is not delivering the value they want. I think if we solve for this as a community of developers, it really sets up AI to have maximum impact. I really feel that way.
Well, I think that's an awesome place to leave it. Like we're building this technology together to make AI accessible to the enterprise, the broadest ecosystem, because it's how it'll be effective for making value and realizing the potential of AI in businesses. And as technologists, I think it's a pretty awesome place to be.
And what better place to do that than here?
Yeah, and in open source. Well, awesome. Really appreciate the time, Brian.
Yeah,
great conversation. Yeah. What a fascinating look under the hood of AI inference with Brian Stevens today. The big takeaway for me, as we push the boundaries of hardware, bringing models to production, the community is helping transform the enterprise AI landscape. It's a story we've seen before, mirroring the open source journey of Linux. Smart, collaborative problem solving, making powerful technology accessible. It shows that progress isn't just inevitable, it's built often by passionate communities sharing their insights and expertise. That blend of ingenuity and accessibility keeps me truly optimistic for AI's next chapter. Thanks for joining the conversation. I'm Chris Wright, and I can't wait to see what we explore next on Technically Speaking.